Right, okay, so this video here is going to be about the iodination of propanone, also called acetone, and it's going to discuss the rate law and end up with a proposed mechanism, which is a kind of different to the ones that you've been seeing so far. Here's the reaction, here's propanone and here's iodine, and it's actually catalyzed by an acid, and you end up with iodopropanone. You've just substituted a hydrogen for an iodine, and you end up with hydrogen iodide HI. But H plus is also a catalyst for the reaction. Okay? Now, the reaction can be followed with the spectrophotometer because iodine gives a yellow-brown solution, and as time goes on, it produces colorless products. So the absorbance will decrease, and it'll go from this color and it'll become colorless. Okay? So it's a good way to follow the reaction. So what you can do is, as a function of time, you can measure the absorbance, which is proportional to iodine concentration, right? This is a Beer-Lambert law, again, that you saw in a previous video. So the reaction is being monitored by following the iodine concentration in terms of absorbance, okay? Now, you have to find, the best thing to do is to find the initial rate, because it's almost straight at the beginning. And you do it for various concentrations of one reactant and keep the other reactants constant each time and in large excess, okay? As we discussed previously. Now, I'm only showing you here the tangent. I'm not showing you the actual curve. Here we have iodine and H plus in large excess, and we're going to test how propanone affects the reaction rate. So here's experiment 1. Increase the propanone concentration, and yes, there is a change. You get a steeper gradient. So all this is showing at the moment is that propanone does have an effect on the reaction rate. Okay, there's the conclusion. Propanone concentration does affect the rate, so it must have an order of some kind. Now we're going to keep iodine and propanone in large excess and change the concentration of H plus and see if that's got any effect. Change the concentration of the catalyst. Okay, and there's experiment 1. Increase the concentration of H plus ions, and yes, the gradient becomes steeper. So therefore, H plus does have an effect on the reaction rate, and there's the conclusion. So far, we've discovered that both propanone and H plus have an effect on the rate. Now, in the final experiment, we are literally going to find out if iodine affects the rate of reaction. So we're starting here in experiment 1, but we'll drop or rise this here, this starting point here, this initial concentration. We'll change it and see if the gradient is affected, okay? So there's experiment 1. Increase the iodine concentration to a higher initial value, and wow, look what's happening. We have a constant gradient. The rate is unaffected. The rate of iodine consumption there, the rate of reaction, the rate of the overall reaction, is unaffected by changes in the iodine concentration. So there's the conclusion. Iodine concentration does not affect the rate. Okay? So there's the 3 mini conclusions. Now here's some actual data, and you've been studying how to use kinetic data in a previous video. So you can see here, for example, that H plus is kept the same, iodine is kept the same, propanone is doubled, and reaction rate doubled. So immediate conclusion is that the order with respect to propanone is 1, first order. Okay? And now you can see another experiment where propanone is kept the same, iodine is kept the same, and you can see that this is going up 30%, and this increases by the same proportion. So it's also first order with respect to the catalyst, with respect to the H plus. Now, you can see that we don't have a place here. This is iodine changing, but this stays the same, but this is changing as well. So it might look a bit awkward, but we already know it's first order with respect to propanone. So that helps. We can ignore this because it's not changing. This is doubling, that's halving, and the rate is halving. This number here, be careful, this number is half of that number. And we know this is first order. So when this halves, which means that this doubling is irrelevant. It's not having any effect. It's not negating in any way. It's not changing the fact that this is halving, because the rate does halve, the rate does change. So therefore it must be zero order with respect to iodine. So we end up with a rate law like this where iodine is not involved. Now if I step back here, can you use any line you like there to work out the value of K? You can choose any experiment. This of course is totally irrelevant. You're going to use the red figures and the blue figures and the orange figures, and you're going to work out any line you like. What is the value of K in the reaction? Right, there's the order. Pause the video now and work out the value for K with units. And here we go. This is the value for K, and of course it's a second order rate constant. Okay. Iodine cannot be involved in the RDS, and now we have to propose a mechanism where somehow it's first order with respect to both H plus and propanone. And a three-step mechanism is proposed. You'll never have to do this in the exam, so don't worry. It's just of interest, and it brings in a new concept that we haven't looked at before. Okay? There's a three-step mechanism which will satisfy the observed kinetics and the equation. And here's the three steps. Okay, just push this out of the way. In step one, the catalyst H plus reacts with the propanone to give this intermediate here with a charge on it. And it's a fast reversible step. We haven't seen this before yet. This intermediate then is broken down into another intermediate and produces H plus. So you can see that that H plus is regenerated. I could cross it out. And this intermediate can be crossed out as well. And now I have this. And then this reacts with the iodine in another fast step to produce the final products. Okay? Now, what's interesting here is that this is the RDS. This is the rate determining step. And in previous videos, we've seen that you look at the chemicals involved in the RDS to get the order. But this is not a substance you can have in a bottle. It's just a high energy intermediate that doesn't last very long. But you can see that this cannot arise until one of those has collided with one of those. So since this and this are the same, I can effectively put these two here in the RDS and say it's first order for that one particle and first order for that one particle. Here we go. That intermediate moves there. I can take those there and cross them out. That intermediate moves there. And I end up with, if I just do this for you now to show you the crossouts, I get my crossouts, then another crossout, and I end up with the overall equation. Propanone and iodine gives these final products in a three-step process. Okay, here I go. I can show you now a three-step mechanism. It satisfies the overall balanced equation and it satisfies the rate law because the slow step effectively involves indirectly one particle H plus and one particle of propanone. And this is indeed catalytic because it's regenerated at the end there. Okay, in fact, the H plus hasn't been used really, has it? Okay, there we go. So then I've blotted out the things that are intermediates, and I've left myself with the balanced equation. Propanone and iodine give us that those products there. Okay, there we are. Thank you.